Hello, everyone. Welcome to Lecture 8 of Compound 50. The plan for today is to talk about recursion. I will tell you what's recursion in this lecture. It's actually a very nice topic. I really like it. And again, I'm going to use the notes by Marianne. And we'll also have, of course, as usual, we have some code examples. Okay, so what's recursion? So before saying what's recursion, so far we've seen functions that sort of, we wrote functions, but we also wrote functions that call other functions. So here's an example. Let's say our main says repeat lyrics. So what's repeat lyrics? It calls this print lyrics function twice. So if we were to run this, and what does print lyrics do? It calls the function print. Well, there should be parentheses, right? So these are notes from an older version. There should be parentheses here. So basically, the function repeat lyrics, it calls print lyrics. And the function print lyrics, it calls print inside. All right. So maybe the picture looks something like this. Repeat lyrics calls this print lyrics. What's a recursive function? A recursive function is a function that calls itself. So basically, this would be the picture. So we have some function called compute, and this function calls itself. Okay, so why is it useful? Well, sometimes there are situations, kind of natural situations, where you have a problem, and what you want to do is decompose it into smaller problems that look exactly the same, but on a smaller input. Okay, so let me skip this rabbit example. So let's say this example of factorial. So what's factorial? A factorial of a number n is the product of the first n integers. Okay, so it's 1 times 2 times 3 times 4 up to times n. Right, so for example, what's 4 factorial? 4 factorial is 1 times 2 times 3 times 4. And I would like to say that, look, we can write n factorial as n times what? Times n minus 1 factorial. Okay, so we have n times n minus 1 factorial. So basically, this calls for a natural definition, and the natural definition says that n factorial is equal to n times n minus 1 factorial for n greater than 0. And when n is equal to 0, then we define the factorial of 0 to be 1. Okay, so you may wonder, why is that? Sort of, I don't know, this is what we really need. So definitely 1 factorial is 1. So we could say that the base case is n equals 1, but even for 0, we usually find it as n 0 factorial equal to 1. Because the reason is that we do multiplication, and in multiplication, 1 is the neutral number, right? It's the one that you multiply and you still get the same result. Okay. So how about we try writing this code? And here I have two examples. So one is called factorial iterative. So iterative is basically, how you would usually write it. So if n equals 0, just return 1. And otherwise, so we define factorial to be 1. And then we say, okay, so how about we do it like this? And here I will write 1 times 2 times 3 times n. So I write it up in range n plus 1, and that's because, range n plus 1 means we go from 1 up to n. Or rather, here, I guess we go from 2 up to n. Okay, so that would be a usual way. And what do? We multiply factorial by I, and in the end, we return the result. And here is a recursive way to write it. So the base case, let's say if n is 0 or 1, we just return 1. Well, I guess we could also do this base case here. And otherwise, compute n minus 1 factorial and multiply it by n. Okay, so we have two different definitions, and if we try to run this code, So how do we run it? We run it factorial of 0 is 1, factorial of 1, factorial of 2 is 2, factorial of 3 is 2 times 3, factorial of 4 is 1, 2, 3, 4, so that's 6 times 4, that's 24, and factorial of 5, and so on. So this factorial grows pretty fast. For example, what's 10 factorial? Well, 10 factorial is already a pretty large number, right? The number is this large. It's 3 million, a bit more than 3 million. Okay, so this is our first example, right? So we can write factorial recursively, and we can write it using iteration. So far, it seems, yeah, what's the big deal? Why do we need these recursions? But I would like to say, for now, it's at least a nice concept. Okay, so this is much cleaner. Okay. Right. So again, this n minus 1 factorial is a subproblem, smaller subproblem that we're trying to solve. And then we multiply it by, by n to get the answer to our question. Okay, so we have the base case, n equals 0, or maybe n equals 1, and then we have the recursive step. Okay, so let's see another example, and this example will be power. So how do we compute a to the power n? Right, so one way to do it is to say, a times a times a n times, just have a for loop. And another way is to use recursions, to compute a to the power n minus 1, and then multiply everything by another a. So here is the recursive definition. So the recursive definition says, if you want to compute a to the power n, if n is 0, just return 1. Okay, so any positive number to the power 0 is 1, except for 0, okay? And if n is greater than 0, then we compute a to the power n minus 1 recursively, and then multiply by a. Okay, so this is how it will work. And the iterative version would be start with 1 and then multiply x by a how many times? N times. Yeah, that also works. Okay, let's see if I have this. Yeah, I have this example here. And in fact, I made this example a bit more complicated. Uh, so here is what we're doing here. I'll have a function called test power that runs first my function called power, this one, and then it will also run the pow function. This is from the math library, and we'll compare the results. Okay, so here is the recursive definition of power. If a is 0, just return 0. Okay, if n is otherwise, if n is 0, return 1. If n is greater than 0, what do we need to do? So we'll compute a to the power n minus 1. Okay, so we need to cast it into float. And then we multiply by a. Right? So this is a to the power n minus 1, and then multiply by a. And if n is a negative number, okay, so for example, a to the power negative 3. So what's a to the power negative 3? It's 1 divided by n cubed. So we define k to be, well, just negative n. And what we return is 1 divided by, so we compute a to the power k, and then we do 1 divided by this number. But maybe what I would like to say is, I would like to put it here, actually. So the first three cases, this is the base case. This is handling the case a equals 0. This is handling negative n, and this is the actual recursion. So let me put it here, maybe the actual recursive call. Okay, so the function is kind of slightly more complicated, but basically this is the recursive call. And all right, let's try to run it. So when we run it, let's see what happens. When I compute 2 to the power 5, so one of them says 25, sorry, 32, right? 2 to the power 5 is 32. And so both of these say 32. And if I compute 2 to the power negative 2, what I get is 0.25. All right. I would like to see maybe one more example. I don't know, 2 to the negative 3, let's say. What will we get? So we should get 1 over 8, which is 0.125. Okay, so that's another example. Okay, so how about we do it like this? So yeah, so I think this is the right order. So this is the base case, this is the recursive call, and these two are sort of cleanup. Okay, that's another example. Play with this example. Okay, so let's try to kind of think in our head what's really going on. So let's say I want to compute 4 factorial. How do we do that? So 4 factorial says compute 3 factorial and multiply by 4. So what's really going on here? Computing 3 factorial calls another function factorial with argument 3, right? And then when it returns, okay, well, yeah, we'll do it in a bit. 3 factorial calls 2 factorial, 2 factorial calls 1 factorial, 1 factorial calls 0 factorial. After we're done, 0 factorial is the base case, so we just return 1. When we return 1, we go back to the color, multiply it by 1. Then we go back to the color of 1, multiply it by 2. Then we go back to the color, we get 6. And then we go back to the color of the original factorial of 4, and we get 24. And that's our final answer. All right, so this is sort of the picture that we should have in mind, that the function calls itself several times into depth and then comes back. Okay, and the rules, I find it really hard sometimes to explain the rules for recursion, but there are some basic ideas. So for example, one basic idea, we should always have a base case. Mhm. That's step one. In both examples that we saw, we had a base case. Then what else do we want? We want the smaller subproblem to be correct. And then given the smaller subproblem, we want to compute the actual solution. So we'll always assume that we get the correct answer for the smaller subproblem, and this allows us to compute the solution, right? We compute 3 factorial, then multiply by 4. And it's important, I would like to emphasize, it's important that the subproblem is smaller. Here's what I mean. So here are two examples of mistakes. So here the base case is wrong, right? Because if we, for n equals 0, return 0, then no matter how many times we're going to multiply this, we're always going to get zeros. But here is a more, okay, here the recursive step is wrong. It should be multiply and not plus. But I think this is the most interesting one. So what's wrong with this example? This example is correct in terms of math, right? So n factorial is equal to factorial of n plus 1 divided by n plus 1. Sure, it's correct mathematically, but we will never reach the base case. So if we run this, we'll basically make more and more calls. We want to compute 4 factorial, we try to compute 5 factorial and 6 factorial and 7 factorial and 8, and we'll sort of go up and we'll never reach the base case. So this function will simply never stop. Okay? So make sure that your recursive calls are always smaller than the original until you reach the base case. Okay, make sure that you reach the base case. Okay, let's see one more example. So let's try. Okay, let's not try not to run code, but to simply run it. So what's count of zero? How do we compute? What happens with count of zero? So first step, we print zero. You know, index is less than two. Yeah, it's zero. So we increase index by one, and we make a recursive call with count of one. Then we print one. One is still less than two, so we're going to call this again with count of two. We print two. We don't reach the if statement, right? We don't the if statement, we don't call it, so we exit. So the program will print 0, 1, 2. And here the base case is that index is greater or equal to. Okay, so usually it goes down, but you can come up with funny examples where the base case is actually not 0, it's 2. So what do you think will happen in this example? Okay, we call count of 3, it will print 3. It will say if index is less than 2, is index less than 2? No, it's more than 2, it's 3. So we'll just exit. So basically this program will simply print 3. Please run it on your own and see that you make sure. Okay, please run a debugger and make sure that you understand what's going on there. Oh yeah, another example is we try to move print from beginning to the end, see how this affects the program. Okay. Here is a standard example that we do in recursion. It's called Fibonacci numbers. So what are Fibonacci numbers? So Fibonacci numbers are defined as follows. So it's a Fibonacci, it's a sequence of infinite sequence of numbers. So the zeroth number is 0 and then 1. And then each number is a sum of two previous. For example, 1 is just 1 plus 0. 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. I think you're getting it at this point. So what's the definition? So we have two base cases. If it's 0 or 1, we just output 0 or 1. And otherwise, we compute Fibonacci of n. How? It's Fibonacci of n minus 1 plus Fibonacci of n minus 2. So we have two base cases, and then the recursive calls. Let's see this example. Where is my Fibonacci sequence? Okay. So here is what we do. So here is how I define my Fibonacci sequence. Fibonacci of 0 is 0, Fibonacci of 1 is 1, and otherwise return Fibonacci of n plus n minus 1 plus Fibonacci of n minus 2. And my test fib, here is what it will do. You know, I'll compute Fibonacci of 5, of 12, and of 30. Let's try to run it. Okay, so it seems to work. But let's say instead of 30, I put 40 here. Okay, so it's a slightly larger number, but not outrageous, right? 40. Hmm. There seems to be some sort of delay. I'm wondering why that happens. Yeah, maybe something went wrong. Let's try Fibonacci of 35. But notice already with 30, something is happening, right? It didn't print the number immediately. With 35, it took it a couple of seconds, right? If I put a 36 here, yeah, there is some sort of delay. So what's going on here? So why is it the case that, and I will put 38, for example. So there's really a delay. Okay, so it seems to be computing the numbers too slowly. Let's try to understand why. Okay, I will not go into the exact thing, but at least let's try. So when we want to compute Fibonacci of 30, what's really going on? So I'm saying we make two recursive calls. We make Fibonacci, oh, well, let's not do 30, let's do just 5. We call Fibonacci of 4, and then we call Fibonacci of 3. Okay, what happens when we call Fibonacci of 4? again, we make two recursive calls, Fibonacci of 3 and Fibonacci of 2. What about this call? Now we compute 2 and we compute f of 1. So I will write fib f and not Fibonacci because it's a bit, it's a bit long. For 3, we compute 2 and 1. For 2, we compute f of 1 and f of 0. It's getting a bit tricky, but sure. I'll make some more space so that we can see everything. And f of 2, that's again 0 and 1. And for f of 1, we will basically stop here. Oh yeah, and there is one more call here. Now, if that was not enough, f of 2 here, again, we compute f of 1 and f of 0. Okay, so that's for this f of 2. Okay, so does this picture, I hope it makes sense to you. Basically what I'm trying to write here is all recursive calls that are made during Fibonacci of 5. So what do you see wrong here? Well, what you see, maybe that will look suspicious. I want to compute Fibonacci of 4, and for that I compute Fibonacci of 3 and Fibonacci of 2. But then I want to compute Fibonacci of 3, I do it again all of a sudden. Right, but wait, I already had the answer. But I don't reuse this answer. Instead, I compute Fibonacci of 3 again. Right, so basically this subtree, it appears here again. Right, this subtree appears here again. And you can imagine what will happen to Fibonacci of 6. Right, if I were to dare to write Fibonacci of 6, that would be a total disaster because, yeah, there would be Fib 5 here. But then there would be Fib 4 here, and then I would need to copy this entire subtree also under this part. Okay? And so. So this was pretty wasteful. And when you have 38 of these, right? It's only 38. So it turns out that the number of calls that we need to make is a pretty large number. So here's a fact. When calling fib of n, we make, well, more than 1.6 to the power n many recursive calls. And what's this mysterious 1.6 to the power n? Let me not go into this exactly, but it's somehow related to the Fibonacci number itself. Okay, it's related to golden ratio and stuff. So, for example, if n is 30, let me pull up my calculator. So we do 1.6 to the power, where do I have my power? I don't have my power here. No, give me scientific calculator. I would like my powers. I would like 1.6 to the power 30. That's well, not that huge number. Okay, that's 1 million calls. But if I do 1.6 to the power 38, that's already 58 million calls. That's a pretty large number. Okay. And I mean, frankly, an optimized laptop should do 1 million operations immediately, but maybe my laptop is not that fast. Either way, I hope you understand this example. So the point here is, recursion is actually very inefficient in the sense that it doesn't reuse the computation, but rather it makes the same computation several times. So instead, here's a non-recursive solution. So this is an iterative solution. So here's what we're going to do. We're going to have a list called save. So save in position I will call fib of I. Okay. So it will be a list of length n plus 1, right? So 0, 2, 3, up to n. Save of 0 is 0, save of 1 is 1. How do we populate the next value? So the next value is populated by simply looking at two previous values, taking their sum, and putting it into the ith value. Okay, so that's the trick. So you want to compute Fibonacci of 2, you look at Fibonacci of 0, this one. You look at Fibonacci of 1, you add them up, and you get your answer. And in the end, what should we return? We return save of n. Let's try. I'm going to call the iterative first and then the recursive. So iterative returns the answer immediately. But recursive of 38, yeah, it takes a while. Okay, so this example says that, okay, we can compute the number iteratively, we can compute the Fibonacci numbers recursively, and in this case, iteration is more efficient, although the recursive seems to be more natural. And there will be examples where recursion is more natural. Okay, so that's our example of Fibonacci numbers. Here's the question, what does this program do? Okay, how about we start it for a bit? So you enter a number n or number x, and you feed it into this function something. And here's what something does. Okay, if n is greater than equal 10, do something. We'll take care of it later. If n is less than, like between 0 and 9, just print n. Just print this one digit. Otherwise, so remember, this means you divide and you only take the remainder. So this is basically printing the unit digit of the number. And then you apply recursion of n divided by 10. Okay, let's try to see this example in the code. Um, if we run it on this number, what we'll get is, so the number is 1, 2, 3, 2, 7, 2. It prints 1, 2, 3, 7, 2, but in reverse order. Okay, let's try to see what's really going on here. Okay, maybe we'll even try to using a debugger. Okay, so we start with number n. N is equal 1, 2, 3, 7, 2. Yeah, it's more than 10. So first we print the digit 2. Okay. And then we make a recursive call on n divided by 10. So remember, this is division without remainder. So when we go inside, n becomes 1, 2, 3, 7, right? So we divide by 10 without remainder, so we get rid of the last digit. Okay, so we got one, we printed one digit and then made it one digit smaller. Okay, n is still more than 10. What will it print now? It will print 10 now. It will print 7. Yeah, here we go. It printed 7. And then make a recursive call again. Okay, now it will print 3. Okay, now n is equal to 12. It will print 2. Make recursive call with n equals 1. With n equals 1, we reach the base case. And we're done. Okay, so now we exit all this. Okay, so let me try to add some comments. This is base case. And this is recursive call. Okay. Okay, so we print the numbers we print the digits in the reverse order. Here is a question for you, so think about it for a second. What if I change the order here? What will it do now? Okay, let's try to print and see what it does. maybe put here number 5 so I don't get confused between the two. So what it does, it prints the digits, but now from left to right. And the reason is we first print, so it prints all digits except for the units. And this one prints the units. So the order says first print all the digits except for units and then print the units digit. Okay, so small change can sort of do the printing in reverse order, right? So do we print first everything and then the last digit, or do we first print the last digit and then everything else? Okay, so that's one more example. And okay, so that was this example. Here's a question for you. Maybe we'll do it later. What does this program do? So let's see. If n is less than 10, just return the number as is. Otherwise, compute the unit digit. Compute something on everything except for the last digit, and then add the last digit. So what do you think it will do? Okay, how about you run it and you see? You know what? In fact, I'm going to run it maybe on one or two examples, and then you will try to guess. Maybe we'll run it on a smaller example, like 75. Oh no, something went wrong. Let me see what. Oh, it doesn't print. We need to return n. And here we want to print the sum. Okay, so here it printed 12. I don't know, if we do 7125, it will print 15. Can you guess what it does? Okay, if it's a single digit, just prints a single digit. But if I do like 4, it will print 8. So, question for you. What does this function do? Or, explain the functionality of this. That's a nice exercise. Okay. Um, okay, let's try to do this example. So here's what we do in this example. In this example, we write numbers in binary. So what's binary? Binary representation of a number, this one represents sort of the units and then the tens and then the hundreds, but we do it only in powers of 2. So this represents the ones and then twos and then fours and then eights. I suppose you've seen some. So basically, binary representation of a number, for example, 13 in binary is, well, 1101, because 1101 corresponds to, okay, this one we multiplied by 1, this one by 2, this one by 4, and this one by 8. So it's 8 times 1 plus 4 times 1 plus 0 times, sorry, plus 2 times 0 plus 1 times 1. Okay, that's together 13. And if, for example, I don't know, I have 111 like this, right, so this number corresponds to, 1 plus 2 plus 4. We skip the 8 because there's 0 here, and here it's 16. So this will be 23. And what we'll do is compute the number in binary. Okay, so it will say print binary 5, print binary of 9, print binary of this large number. And here's how we do that. Uh, so here's what it does. We first, as a base case, if n is 0 or 1, we just return the string 0 or the string 1. Otherwise, we compute only the last digit. So here's what it means. If n is even, it returns 0. If n is odd, it returns 1. And otherwise, we divide by 2. We compute, so basically dividing by 2, divide by 2 corresponds to dropping the last digit in the binary representation. So the last means rightmost digit. And apply recursion. Okay, so for example, let's try to run it on 13. Maybe we'll do it recursively. So, we know that the representation of 13 is 110. Here is what we're going to do. So n is 13. Okay, so is n 0 or 1? No. We're going to n divided by 2 will correspond to 6. So 6 in binary is only the 110. It's only these 3 digits. Right? So n is 6. It's only 3 digits. When we divide by 2 again, what are we getting? We're getting 3. 3 corresponds to only these 2 digits. Only these 2 digits. Okay. We make a recursive call. Yeah, then we make another recursive call when n is 1. When we return, we start printing all these digits one by one, right? So we first print, well, we don't print, we kind of accumulate into a string. So we first collect this 1, and then another one, and then 0, and then another. And the result will be 110. So this is how we compute the binary expansion of a number. So let me try to run this one example. So when we run binary on 13, so 13 is I don't know how I should do it. So this responds to this in binary. So then we make a recursive call on 6, where what's 6? 6 just drops this one digit. This one makes a recursive call to 3, which drops one more digit. This corresponds to 1, which drops one more digit. And this is the case. I hope this example makes sense. Okay. So I would like to summarize. So, we have recursion, we have iterations, and iterations sort of use for loop and while loop. Recursion can also be, can emulate for loops, but it sort of works in a different way. So we sort of have a base case, and then we have recursive call. And remember, the recursive call must always be smaller than the base case. Okay, and the goal in recursion is to divide the problem into smaller subproblems and then solve smaller subproblems, and using that we get the actual problem. Right, and we saw examples like this Fibonacci where the overhead may be more complicated, but on the other hand, the code looks very clean. So it's a trade-off. Let me give you one more example before we finish. I'll call this what, and this is what it will do. So I'll call the function what. And here's what it does. So this is one last example for today. If n is less or equal 1, oh, just return 1. Okay, nothing to be done. Here's what we do otherwise. We define k to be n divided by 3. Okay. And then we return what of k plus what of n minus k. Let's divide by 2 complex. So for example, what will be what's the output of 2? Oh, something's wrong here. And let's print the result. Okay, so the output of 2 is 2. The output of 1 is, well, obviously 1. What will be, for example, q? What is compute what of, I don't know, 15? And explain the functionality of what. All right, that's all for today. Thank you.